Hello and welcome to the third of our online tutorial sessions for Advanced Mechanical Principles. And this is the final outcome on kinematics, you may be pleased to know. And we're looking at the merit task now, which is the quick release or quick return mechanism. Quick return mechanism, an interesting application of converting rotational energy into translational energy or linear movement, with where the outstroke is often a different speed to the instroke. So just to start us off, I've got this video from Skyline Tutorials. Forgive the music in there, but you'll hopefully see what I mean by a quick return mechanism. So what we see is that the outstroke and the instroke is faster than the outstroke. Okay, and that's all set up by the fact that our rotational part has got a slot where a pin can slide in. Okay, so we're going to be analysing this system today. Okay, that's all I wanted to show you on that. So if we come back to what we're going to look at today, then what we're going to look at, to do this analysis, you will need a calculator, you'll need a protractor again, you'll need a rule again. The protractor is not as vital in this one. The scale drawing isn't necessarily important to draw. We will be doing mathematical analysis of it, but you can always check your answer with a rule if we do a scale drawing. So what we're going to look at is another one of the worked examples from Free Study. This is quick return mechanism worked example number 6. So we'll see that there is a force acting on this. We actually ignore that, we're not using that for what we want, it's just in the diagram. This crank is rotating at 100 radian per second, so this time we've already done the conversion, we don't need to do anything with that angular velocity. We're going to be analysing when the angle theta is at 60 degrees and we have various dimensions on the diagram. Okay, so how do we go about analysing? And what we're being asked to find is the angular velocity of BC, and once we found the angular velocity of BC, determine the translational velocity or the absolute velocity of C with respect to B. Okay, so once again we start and we're going to draw some triangles. So starting off, and I've done this to scale, we have section OA, which is 40 millimeters long at an angle of 60 degrees to the horizontal. Okay, and point A is where the pin of our quick return mechanism sits within the slot of bar BC. So we've drawn that. We now add bar BC in and we get this. So point A is somewhere along the middle of this bar, but we don't know where. Okay. We will need to know that distance to complete this task, and we'll be working that out momentarily. We also know that point B is 70 millimeters away from point O along the same plane, and these 2 points are fixed. These don't move relative to each other. So once again, just like in the last exercise, point O and point B will be the same point in our velocity diagram. That's important. We're looking at point C, but we have to do all the work with point A first. So how do we determine this angle alpha? Okay, so the first thought is, well, I've got two sides, two lengths. I've got the angle between the two lengths, so I could work out length AB. Then I've got two sides, three sides one angle so I can work out the second angle. But there's actually a faster way to do it, which uses Pythagoras' theorem. Okay, so to use Pythagoras' theorem, what we do is we take this line OA and we create a right-angled triangle using that as the hypotenuse. From that we can then see that, hopefully, if you all remember your work on Pythagoras' theorem and trigonometry, that 40 millimeters times the sine of angle 60 will equal this length, and that length is equal to 34.64 millimeters. Similarly, this length here is going to be 40 millimeters times the cosine of 60, and that comes out to be 20 millimeters. Now if we look at this logically, what we've got is we have a right angled triangle where that is 34.64, that is 90 because we have 70 here plus 20 here to make 90 in total. And therefore that angle can now be worked out, and length BA can also be worked out. So we'll do both of those over in this side. So quick, first one is the angle alpha. That is equal to the inverse tan of 34.64 over 90. That is equal to 21.25 degrees by my calculator. Similarly, using Pythagoras' theorem, length BA is equal to the square root of 90 squared plus 34.64 squared, which is equal to 96.44 millimeters. These two values we need for the next step of our task. Okay, so we need to make sure that they are in. Okay, now we've got the space diagram, and this is drawn to scale, so we can measure things. I'm going to go into another package, okay, and we're going to start drawing tangents to this system. Okay, so you should now be seeing our space diagram in Smart Notebook. Okay, so what I'm going to do is I'm going to take my rule and just show you that things are to scale, or will be to scale. So if I'm 70 millimeters, then I want this rule to line that to be 70 millimeters. Okay, if I do that, fortunately I have a protractor on the bottom of my rule. I found that the other day, so that's useful. You can see my 40 millimeters is near enough correct, and if I come to the 21 degrees, my BC is just slightly short, so I will just extend. Oh, I can't extend that line. Apologies. Okay. But what we can see from here is that BC is 96 millimeters long, or BA is 96 millimeters long, which is what we calculated it to be. Right, so from this we now need to draw, because we're getting the tangential velocity, we need to draw the tangents to the lines. So I've got my protractor already, set my protractor's 90-degree line across OA, just like we did before. Get your pencil, mark your horizontal points, and then draw yourself your tangent to this curve. I'm going to do it very thin today so that it's not too imposing on what we're trying to do. I'm not drawing anything to scale here, I'm just drawing the tangent line in. Okay. Similarly, and as we did last time, we'll also have a tangent line for BC or BA, because it's effectively the same plane. So again, I want that tangent line to be drawn in. Okay. So in essence, what we get is, just bear with me 1 second while I make that one thinner as well. So in essence, what we get is 2 lines. Now the problem is where we get the third line from, because these 2 points now are actually fixed. While they're on the same plane in a crank slider, B is still moving horizontally. But in this system, B and O are fixed. And what we do is we actually draw this BA line in again. And I'll explain that as I draw the diagram on the next sheet. So we're going to take these tangent lines and we're going to build the velocity diagram. Okay. From it we'll get some angles and we'll use Pythagoras to determine the solution. So we're going to start here, and what I've already got is point O and point B as my origin, and I've drawn to scale, which should be 30 degrees, my 4 meters per second to be 8 centimeters long. So I'm just going to put in there, make that 12, 4 meters per second. Coming off that as well, we have the member BC, which is coming at 21 degrees. So I'm going to put my protractor on point O, which is also point B. Determine my line again, and again I'm going to change the colour of this line to be red. And I'm just going to draw in 10, 20, 21 degrees through that point. Okay, and I know I'm going to want that line slightly longer, so let's make sure I keep that 21 degrees, but I'm going to make the line as long as I possibly can. Finally, don't move that line. What we want to do is move the protractor, and we're going to take 90 degrees of the red line we've just drawn. It should be somewhere. Okay, now I'm going to take that 90 degrees. Now I'm looking at that, and I can extrapolate that, I actually need my protractor to be slightly further up. Okay, or once we have our angle, can I get my protractor there? Yes, I can. Because what we want it to do is meet OA. So I'm going to put our third line in here. Okay, and we're going to put this one in a light blue. Okay, and again, just bring it down like that. Right, now what that's done is created a triangle. We can measure the angle here, but we actually don't need to measure it because we can calculate it. Okay, but we can measure this angle here. It's going to be 51.25 degrees. I know it's going to be 51.25 degrees because if I take the horizontal line, I'll use my rule to give the horizontal. We know that this angle above the horizontal is 30 and this angle below the horizontal is 21.25. So what that means is this angle here is 51.25 degrees. We also know that this angle is 90 degrees. And so what we're going to do is call this point A1. Okay. Now A1 is a point in space where the velocity of A with respect to B can be determined. Okay, so what we want to know is this length of A to A1. Okay, so I can calculate it or I can measure it and we should get the same answer. So measuring it, I'm coming out at 6.22, 6.23 centimeters. Okay, so by measuring it, remember my scale was 1 centimeter to 0.5 meters per second to 1 centimeter. So looking at this, I halve that value and I'll have 3.12 meters per second. Similarly, as I know this angle is 51.25 and I know that this is a right angle, let's try putting a right angle in there, this should be fun. And I know that this is a right angle, I can determine this angle to be 38.75 degrees. And what I'm going to do is, that didn't work. Here we go. 38.75 degrees. Now if I'm after this length A to A1, then I can use simple trigonometry, SOHCAHTOA, to say that 4 meters per second times the cos of 38.75 is equal to that length. Okay, and that is what I'm hopefully going to do here. Now this is where I've never tried this before. No, it didn't work. on the block, we're going to take those values and we're going to say that length A. So the velocity of A with respect to B is equal to 4 meters per second times the cos of 38.75 degrees. And that answer comes out to 3.12 meters per second. But that is the tangential velocity. We are asked to find the angular velocity. Now, fortunately, earlier in the task, we calculated the length of BA. Because always remember that angular velocity is equal to, angular velocity times the radius is equal to tangential velocity. So tangential velocity divided by the radius will give us the angular velocity. Our radius is 96.44 millimeters. So our angular velocity of BC is equal to 3.12 divided by 0.096, which is 96 millimeters. That gives us an angular velocity of 32.5 radian per second. That there is what you need to do to answer part A, okay, with the numbers that are on the assignment sheet. Now, the beautiful thing about angular velocity is it doesn't matter what the radius is. So our radius could be 10,000 kilometers. Okay. Every point on that circle would still be rotating at 32.5 radian per second. Okay. This is actually where flat earthers sometimes fall down. They don't understand what tangential velocity is. Okay, you guys do now, so you can understand. The Earth rotates one rotation per day. It doesn't matter where on the Earth's surface you stand, you always rotate at one rotation per day. Okay. Now, you don't feel like you're traveling at 1,000 miles per hour, partly because there's no acceleration, but because one rotation per day is actually a very, very slow speed. Because the Earth's diameter is roughly 10,000 kilometers, then the absolute velocity you have on the Earth's surface is an enormously huge number of meters per second. I'm not going to try and work it out in this lesson. Okay. But because that angular velocity is the angular velocity of that beam regardless of where we are on the beam, what we then have to do is work out what the absolute velocity of part C is. And that is straightforward because we've already said here absolute velocity is angular velocity times the radius. We know how long the beam is. The beam is 180 millimeters long from B to C. So the velocity of part C with respect to B is equal to 32.5 radian per second multiplied by 0.18 meters to give us an absolute velocity for point C of 5.8 0.85 meters per second. And this is a good example of how that tangential velocity changes just by changing the radius. Rotating at the same speed, but two different absolute velocities depending on the diameter of the rotation. Okay. You should now be able to complete all of that assignment. This is my last day working before Easter, so I am not at work for 2 weeks. I will see emails occasionally if you wish to email them to me. After Easter, that first week back after Easter, I would like this assessment completed, and I would like you to do your best to email it to me in some form, either JPEGs of your handwritten stuff or typed assignments. Okay, I'll put all this on an email to everybody. Hope you're finding this useful, and I'll speak to you again soon.